Hello guys, this is Team Helixpace. In this video, we will talk about why and how we make Helixpace. In today's world, with the huge amount of data that we generate on a daily basis, a demand of effective storage technique is increasing. The genetic material DNA has garnered considerable interest as a medium for digital information storage because its density and durability are superior to those of existing silicon-based storage media. For example, DNA is at least 1,000-fold more dense than the most compact solid-state hard drive and at least 300-fold more durable than the most stable magnetic tapes. Given the benefits of DNA storage, the goal of our project is to provide a new way of storing medical data by developing an algorithm that encodes and decodes DCM files to DNA sequences. The DNA sequence that we will create consists of 4 parts. They are private primer, patient info, images, and public primers. Private primer are generated from user input, username, and password. Patient info section is information read from the DCM files, including patient name, patient ID, and etc. Images part contains the voxel information of the image or images that the user wants to save. The final public primer section are primer generated by hospitals or the doctors.
So our code has particularly 2 classes, and one of them is the primer encoder class, and I was in charge of writing it. Briefly speaking, primer encoder class is the object that establishes basic functions for creating forward primer for DNA storage, so that you can see the first 5 functions, except the initial functions, are the functions that changes string, binary, sequence data into one another using for loops. The progress of encoding is string to byte decimal, decimal to binary, and binary to sequence. So if you check binary to sequence function, 00 is correspond to A, 01 is to T, 10 is to C, and 11 is to G. And we have the 3 testing functions that check if the raw primer sequence can actually function as a forward primer. First function is for checking if the primer sequence is accidentally having a same sequence with the other converted data, which can happen very rarely. And the second function checks the melting point of the sequence and check if the melting point difference is more than 12 than that of the public primer. If so, it returns false, as having 12 degrees Celsius difference of melting point will have problem during the PCR. And finally, third function that checks if GC component is between 40% to 60%. Actually, these 3 checks are not a complete verification of the efficient forward primer, like we still need to check the structure of the self-dimer and hairpin formation of the sequence, so that can be an improvement for the future development. And another thing we could improve more about this is making an algorithm that optimizes the converted sequence to satisfy the check functions, or like even tests if substring of the generated sequence can be the unique primer that can function as a forward primer.
For the patient information part, firstly we talk about encode. We store the patient information that we have gotten from DCM file, such as patient ID, patient name, patient birthday date, patient age, and patient sex. Then we change the string of patient information into ASC code. After finishing transferring to ASC code, we change them into quaternary code, which could combine with ATCG in DNA. Therefore, we could construct a guide, then the string of the patient information could be stored as ATCG in DNA sequence. In the decode part, this is very similar to the encoding process. Firstly, we need to build a connection between the ATCG with the string of the patient information. We need to let the DNA sequence which stores the patient information be changed into quaternary code. Therefore, when we get the quaternary code, it could be easily for us to restore the patient information.
The program has two functions related to the image treatment, encoding and decoding. For the encoding process, DCM files stores images as bitmaps that each pixel has a number representing the grayscale at the pixel. First, the numerical pixel arrays of the loaded DCM files are extracted, and the size of the image in X, Y, and Z directions are saved. For each size number and each number in the array, it is converted into a 8-digit nucleotide sequence in order. You can consider this process as you convert a decimal number to a quaternary number, but the numbers 0, 1, 2, and 3 are replaced by A, T, C, and G respectively. The first 24 nucleotides of the encoded DNA sequence store the size of the 3D image. Then all the numbers in the pixel arrays are converted into 8 nucleotide long DNA sequences and connected in order to form the DNA sequence for the image information. For the decoding process, the first 3 8 nucleotide long DNA sequences store the X, Y, and Z lengths of the 3D image. In the following DNA sequence, each 8 bits represents one number in one position of the array. The DNA can be decoded back into a number as a reverse process of the encoding process. You can think you convert quaternary numbers represented by A, T, C, and G to decimal numbers. The image can be reconstructed based on the image array that contains the grayscale of each pixel. The image array can be stored for further treatment, and the image will be outputted into the output folder as PNG files. The last section of our DNA sequence is the public primer section. The main purpose of this section is for allowing users to do PCR analysis on our DNA sequence. This last section also acts as a signature that enables users to trace back the source of the files that they store. Now, without further ado, I will show a quick demonstration of how to use Helixpace to encode and decode your data. You are now seeing the home page of our software. From here, you can go to the encoding page or the decoding page. For now, I will show you how to encode first. In this page, users are required to set up a username and password, and this information will later be encoded to the private primer section of our DNA sequence. Our code will do an efficiency check for every combination of username and password. For example, simple username and password will not pass our check since simple combinations cannot be encoded to efficient primers. Users can only proceed to the next step if they pass the check. The next box is for when users want to store some extra information, and this is where they want to put it. For the public primer section, users can either type in the primer sequence or they can upload a text file from their local computers. Finally, users will need to upload their DCM files by clicking on this button. After done filling in the boxes, users can hit enter and they will get a DNA sequence right here. Next, I will show you how to decode your DNA sequence back to human-readable information. To do that, you would need to go back to your home page and click on the decoding button. In this page, users will need to first upload their DNA sequence and enter their username and password. After this is done, Helix will verify whether the users got the correct combination of username and password. If the combination is correct, Helixpace will then output the result in 3 files. They are extra information text file, patient information text file, and PNG images of the DCM files. Thank you for watching our video. I hope you enjoyed it.